The TeleOR system, a groundbreaking telemedicine innovation, is designed to reconstruct and transmit real-time operating room scenes for remote surgical guidance. This system addresses the unique challenges of operating room scenes, such as high-fidelity reconstruction, obstacle avoidance, and bandwidth limitations. TeleOR introduces three novel approaches that set it apart from other systems. Firstly, dynamic self-calibration leverages inherent scene features for calibration, eliminating the need for preset markers and enabling obstacle avoidance and real-time camera adjustment. Secondly, selective OR reconstruction focuses on dynamically changing scene segments, reducing reconstruction complexity. Lastly, viewport-adaptive transmission optimizes data transmission based on real-time client feedback, efficiently delivering high-quality 3D reconstructions within bandwidth constraints. Comprehensive experiments on the four-door surgical scene dataset demonstrate the superiority and applicability of TeleOR, showcasing its potential to revolutionize tele-interventions by overcoming spatial and technical barriers inherent in remote surgical guidance. The paper emphasizes the significance of telemedicine in extending specialized medical expertise to remote surgeries, where immediate expert guidance is crucial. It cites previous studies that have utilized technology to broaden access to medical expertise, highlighting the transformative potential of telemedicine in this field. Telemedicine plays a pivotal role in providing timely expert guidance for remote surgery, bridging the distance gap between specialized professionals and patients in need of immediate treatment. In surgical intervention scenarios, telemedicine systems require a series of critical steps, including on-site scene reconstruction, transmission, remote rendering, and intervention. Achieving real-time reconstruction and transmission is a significant technical challenge, particularly in surgery, where real-time responsiveness is paramount. Previous research has employed multiple static RGBD cameras to capture and enhance 3D scene reconstruction, modeling scenes by separate point clouds from per-camera viewpoints, and fusing them into a common reference frame using intrinsic and extrinsic parameters. Other methods have utilized neural implicit functions and generative models to achieve higher fidelity reconstructions. However, these approaches typically rely on sophisticated algorithms for robust visual feature extraction and multiview calibration, often conducted in offline settings. Simplifications to enhance reconstruction efficiency have compromised accuracy, making them only suitable for static scenes rather than dynamic surgical scenes. Moreover, these approaches may restrict the number of remote clients who can access the system, limiting their applicability for tele-intervention in surgical settings. The operating room presents a dynamic and complex scenario, posing challenges in scene understanding due to obstructions from large devices, hanging monitors, and moving staff. The balance between high-quality reconstruction and efficient real-time transmission underscores the significant challenges in surgical tele-intervention. To address these challenges, this work proposes TeleOR, a real-time full-scene operating room scene reconstruction system for tele-intervention. TeleOR introduces innovative solutions, including dynamic self-calibration, which leverages the OR scene's inherent features as reference points for calibration, eliminating the reliance on preset markers or physical calibration tools. This technique enables cameras to move and self-calibrate in real time, effectively avoiding obstructions. The TeleOR system introduces two key strategies to address the challenges of real-time remote operating room reconstruction. Firstly, selective OR reconstruction focuses on identifying and reconstructing only the dynamic areas of the OR scene, simplifying the reconstruction process and reducing unnecessary computation on static parts. This approach enables the system to concentrate on the crucial aspects of the scene that require attention. Secondly, viewport-adaptive transmission is a novel strategy that capitalizes on real-time feedback from the client, specifically viewport information, to selectively transmit and render only those segments of the scene that the user is likely to view. This technique ensures the transmission of high-quality 3D reconstructions in real time, even in bandwidth-limited scenarios, making it particularly suitable for underdeveloped regions with limited network resources. The TeleOR system is comprehensively evaluated on the four-door dataset, focusing on reconstruction quality and transmission efficiency under various network constraints. The results demonstrate that TeleOR achieves high-quality reconstructions and maintains real-time performance, even in bandwidth-limited scenarios, highlighting its effectiveness and reliability for tele-intervention applications. In the context of related work, operating room reconstruction is a crucial advancement towards computer-assisted surgical interventions. Previous approaches, such as Osoy et al.'s 4D surgical scene dataset and Jarrett's et al.'s application of neural radiance fields for dynamic scene reconstruction, have laid the foundation for advanced surgical intervention. However, current approaches have yet to achieve real-time remote surgical intervention, a critical capability for enabling professionals to conduct remote surgical interventions. Virtual reality-assisted intervention has also been explored in previous research, with systems capable of tracking the laparoscope's pose and reconstructing the 3D surface structure of organs. However, a gap remains in real-time remote interventions based on reconstructed OR scenes, particularly for underdeveloped regions with limited network resources. TeleOR addresses this gap by enabling real-time remote operating room reconstruction and transmission, making it a significant contribution to the field. The TeleOR system introduces a novel approach to remote surgical observation by integrating multi-view self-calibration, selective OR reconstruction, and viewport-adaptive transmission. This fully immersive teleconsulting platform utilizes RGB and depth sequences captured from multiple cameras to provide real-time visualization for remote professionals. To ensure accurate scene reconstruction, the system employs a multi-view self-calibration process that utilizes orb features extracted from the first frame of each camera. These features are used to establish camera positions relative to one another, resulting in a transformation matrix that aligns the reconstructed scene with the reference coordinate system. This calibration process is critical as it maintains accuracy throughout the surgical procedure, even when camera positions shift due to obstructions or movements of medical staff and equipment. In addition to calibration, the TeleOR system incorporates selective OR reconstruction, focusing on updating only changing scene segments in real time. This process leverages optical flow difference and orb features to detect motion and identify areas requiring updates, thereby reducing data transmission while preserving the quality of the teleconsulting experience. Furthermore, the system's viewport-adaptive transmission strategy optimizes data transmission by predicting the next viewport based on the user's current viewing direction. This approach ensures that only relevant data is sent, minimizing latency and enhancing the overall remote observation experience. In summary, the TeleOR system harnesses cutting-edge technologies in computer vision and machine learning to facilitate immersive and efficient remote observation of surgeries. By addressing challenges such as camera obstructions and bandwidth limitations, it provides a high-quality teleconsulting experience for remote professionals. The TeleOR system leverages real-time updates of camera positions to ensure precise and synchronized scene capture within the operating room (OR) system. This is achieved through the optical flow method, which tracks changes in camera pose by estimating the motion of feature points across frames. Continuous analysis of optical flow vectors enables dynamic adjustment of the camera's calibration parameters. The OR scene is characterized by static objects for most of the surgical process, allowing for selective reconstruction of the scene. The proposed approach focuses updates only on the changing parts of the scene, leveraging an optical flow-based motion detection method. This selective reconstruction pipeline is illustrated in Figure 2, where the RGBD stream from each field of view, FOV, is divided into n times n channels, producing n times n tiles per frame. During the reconstruction process, the interframe disparity of each tile is examined by calculating the cumulative magnitude of the optical flow field difference, DC, with the previous tile at the same position. To reduce computational cost, sparse optical flow calculation is employed using the Lucas-Kanade algorithm, which is based on two assumptions: brightness constancy and small motion. The calculation of the optical flow vector, ArXiv, Vxy, for point x, y, between two consecutive tiles is achieved by solving equation 1, which takes into account the brightness constancy and small motion assumptions. Overall, this approach enables efficient and accurate reconstruction of the OR scene, focusing on the dynamic regions of interest while reusing already reconstructed content. The authors propose a methodology to identify tiles with perceptible visual changes, considering adjustable threshold values based on available computational and transmission bandwidth resources. This is achieved by calculating the cumulative magnitude of optical flow difference, denoted as dc, between two consecutive tiles Tn and Tn plus 1. The calculation is represented by equation 5, where mount x, y is the magnitude of the optical flow difference for point x, y, and n width and n height represent the width and height of the tile, respectively. The optical flow difference magnitude mount x, y is computed using equation 6, involving the square root of the sum of squared horizontal and vertical optical flow differences, u2xy and v2xy, respectively. If the cumulative magnitude dc exceeds a set threshold theta, the corresponding position in the RGBD frame is masked, and the partially masked frames are forwarded to the synthesis server for conversion into point clouds. The authors employ a tile-based selective reconstruction approach, where corresponding sections of the scene are not regenerated for masked tiles within each frame. Instead, previously generated segments in the preceding frame are retained and reused. Additionally, a viewport-adaptive transmission mechanism is introduced, leveraging real-time feedback from the client, specifically viewport information, to adaptively load data for transmission. An efficient LSTM network is employed to predict the user's field of view, FOV, for the next time step, based on gathered data on past FOV movements. This prediction enables the strategic synthesis of point clouds solely within the predicted FOV, ensuring efficient utilization of bandwidth by transmitting and rendering only the scene segments likely to be in the user's view. To prevent prediction failures, a prediction range of 120 degrees is used, expanding beyond the typical user's viewing frustum, which not only covers a wider area for improved situational awareness but also strategically reduces the point cloud density from the center of the predicted FOV to minimize data usage. The seventh page of the research paper delves into the TeleOR system's adaptive capabilities in real-time remote operating room scenarios, leveraging predictive modeling and bandwidth management to ensure high-quality 3D content delivery under varying network conditions. Table 1 illustrates the reconstruction quality assessment across different network conditions, including limited, medium, and adequate bandwidth. As bandwidth increases, reconstruction quality improves, with optimal results achieved at an adequate bandwidth of 100 megabits per second. The authors detailed their experimental setup, utilizing the public operating room dataset 4-door for evaluation. This dataset comprises 6,734 scenes captured by 6 RGBD Connect sensors. Evaluation focuses on two key aspects: reconstruction quality and transmission efficiency. TeleOR's implementation is built on top of Open3D, deployed on 6 edge computing devices connected to a synthesis server via Wi-Fi. A real-time player is constructed on top of Unity and deployed on a Meta Quest Pro head-mounted display. The paper concludes by discussing the assessment of visual quality using the Structural Similarity Index metric, SSIM, for analyzing 2D renderings derived from the reconstructed 3D models. This metric provides insight into how well the system maintains image quality despite varying network conditions. The performance of TeleOR is evaluated in terms of reconstruction quality, transmission efficiency, and ablation study. Reconstruction quality is assessed using multi-view SSIM, MSSIM, and scene reuse ratio, RUS, metrics. Under a 20 megabits per second bandwidth, TeleOR achieves a high RUS of 85.8%, indicating significant reuse of segments reconstructed from previous frames. This reduces the complexity of the reconstruction process, ensuring real-time performance. Figure 3 demonstrates that TeleOR maintains high-quality reconstructions at 100 megabits per second and acceptable performance under severe bandwidth restrictions, ensuring visual quality in real-time reconstruction in bandwidth-constrained environments. Transmission efficiency is evaluated using frames per second, FPS, and latency metrics. The evaluation is conducted on all 10 groups of 4 DOR, each containing 3,000 sample frames for simulation, under the same network constraints as Section 4.2. Table 2 shows that TeleOR maintains a frame rate of 22.7 fps, despite operating under severely constrained bandwidth conditions. An ablation study is conducted to explore the effectiveness of TeleOR's key designs, specifically the selective reconstruction and viewport-adaptive strategy. Table 2 reveals that without these components, there is a noticeable drop in FPS, even under adequate network resources. This emphasizes the critical role of TeleOR's core components, especially under poor network conditions. The authors conclude by highlighting the significance of TeleOR, a real-time remote operating room system designed to enhance tele-intervention through high-fidelity scene reconstructions. TeleOR incorporates dynamic self-calibration, selective reconstruction, and viewport-adaptive transmission to address issues like camera occlusions, scene complexity, and bandwidth constraints. Experimental results on the 4-door dataset demonstrate exceptional reconstruction accuracy and superior transmission efficiency under strict bandwidth limitations. The authors present a comprehensive list of novel methodologies for optimizing complex systems, focusing on the integration of machine learning algorithms with traditional optimization techniques. This integration enables the identification of optimal solutions by leveraging the strengths of both approaches. The methodologies are demonstrated through case studies in various fields, showcasing improved efficiency and performance over traditional methods. In the realm of telepresence surgery, TeleOR presents a novel approach to real-time remote operating room systems. Building upon the foundations of optical flow-based motion estimation, this system leverages the Lucas-Kanade method to facilitate accurate and efficient tracking of surgical instruments. The TeleOR system consists of a client-server architecture, where the client side is responsible for capturing and processing video feeds from the operating room, while the server side handles the rendering of the virtual environment and communication with the remote surgeon. This enables a seamless and immersive experience for the remote operator, allowing for precise control over the surgical instruments. The system's efficacy is further enhanced by the incorporation of augmented reality (AR) adaptations, as demonstrated in previous works such as laparoscopy with augmented reality adaptations. This integration enables the remote surgeon to visualize vital patient information and receive real-time feedback, thereby improving the overall quality of care. The authors draw inspiration from various sources, including Yeager's work on optical flow-based motion estimation using the Lucas-Kanade method. This method is particularly suited for TeleOR, as it enables the system to accurately track the motion of surgical instruments in real time, even in the presence of noise and occlusion. TeleOR's real-time capabilities are made possible by the efficient processing of video feeds on the client side, which ensures a latency of less than 100 milliseconds. This is achieved through the use of optimized algorithms and hardware acceleration, allowing the system to maintain a high frame rate and responsiveness. The system's performance is evaluated through a series of experiments, which demonstrate its ability to accurately track surgical instruments and facilitate remote control. The results show a significant reduction in latency and improved precision, making TeleOR a promising solution for telepresence surgery.